This video is about 3x3 rotation matrices. So in a previous video, we saw that when you have a 2x2 orthogonal matrix, it's either a rotation matrix or a composition of a reflection and a rotation. And in this video, we're going to look at 3x3 rotation matrices. So for instance, let's say that you wanted to find a matrix that rotates about the z-axis by theta degrees counterclockwise. So in other words, you have this plane, you have the z-axis like this, and you want to take a vector, let's say v, to what you get when you rotate by theta degrees. So you want this to be tv. Okay. Tv and v should have the same length, right? So maybe more like that. The question is, what matrix does that? And it's going to keep the z-axis where it is. Well, if you think of, so here's the x-axis, here's the x1 direction, here's the x2 direction, here's the x3 direction. We can think about it like this. We can look at where 1, 0, 0 goes. So where's t of 1, 0, 0 going to go? Well, the third component will be 0, but when you look at the first two components, right, you're going to multiply that point is going to be rotated by theta degrees counterclockwise. And so you're going to apply, okay, like the first two components are going to be cosine theta, sine theta, negative sine theta, cosine theta, times 1, 0. That's the first component. The first two components of the output. Because what happens is that the third component stays a 0, right? I mean, when you take a point on the plane z equals 0, and you're rotating about the z-axis by theta degrees, the z value stays 0. And what happens to the x and y components? That vector gets rotated, right? So the output will be cosine theta, sine theta, 0. Similarly, if you look at t of 0, 1, 0, okay, you have the third component being 0, and the third component's still going to be 0. So you're basically taking the vector 0, 1, and then rotating that by theta degrees. And the result will be negative sine theta, cosine theta. So t of 0, 1, 0 is negative sine theta, cosine theta, 0. Okay, and what about t of 0, 0, 1? Well, 0, 0, 1 stays where it is, right? Because when you rotate about the z-axis, you're keeping the z-axis where it is. And t of 0, 0, 1 is therefore 0, 0, 1. So now that we know where t maps the standard basis vectors, we can figure out the standard matrix. The matrix A is going to be the 3x3 matrix whose first column is t of 1, 0, 0. That's cosine theta, sine theta, 0. The second column is t of 0, 1, 0. That's negative sine theta, cosine theta, 0. And the third column is t of 0, 0, 1. That's 0, 0, 1. Okay. So that's the first example. What if you wanted to rotate by theta degrees about the x-axis? So now, so here's x1, x2, x3. This time we have the x2, x3 plane, right? That's like the yz plane. And we take a vector here, and we want to rotate by theta degrees to get a vector there. Okay. Well, it's similar. This time we're keeping, let's see, what's going to happen to 1, 0, 0? Well, that will stay where it is, right? 1, 0, 0 is 1 along the x1 axis. So that's not going to change. What about 0, 1, 0? Zero, 1, 0 has first component 0, and the 1, 0 part will go to cosine theta, sine theta. And for 0, 0, 1, the first component will still say 0. It will stay 0, and then the 0, 1 part will go to sine, it will go to negative sine theta, cosine theta. So this is counterclockwise. And similarly, if you rotate by theta degrees about the y-axis, it's counterclockwise about the y-axis. This is if theta is positive, right? If you wanted to rotate by theta degrees where theta is positive and you want to go clockwise, then you would just replace theta by negative theta. Okay, if you wanted to rotate by theta degrees counterclockwise about the y-axis, similarly, the y value stays where they are. So 1, 0, 0 goes to cosine theta, 0 sine theta. 0, 1, 0 goes to 0, 1, 0. And then 0, 0, 1 goes to negative sine theta, 0 cosine theta. Okay. You know, I encourage you to think about why this is true if you're not sure about this. Okay. What if you wanted to rotate about an axis that wasn't the x, y, or z axes? This is a more interesting question. So what if you wanted to rotate along the axis, along the line 1, 1, 1? So you have this line 1, 1, 1. I don't know, maybe it's like this. Okay. And you have this plane that's orthogonal to 1, 1, 1. So here's 1, 1, 1. And you have this plane that's orthogonal to 1, 1, 1. And then you take a vector and you want to rotate. So you take the vector on this plane and you want this vector to be rotated by theta degrees. Okay. And you want the axis that's along this line 1, 1, 1 to stay where it is. So now the question is, what matrix does that? So what matrix rotates about the 1, 1, 1 axis by theta degrees counterclockwise? Well, this one's much harder because it's not easy to see where the standard basis vectors go, right? And that was our strategy to figure out A. And just to clarify, when we're rotating by theta degrees counterclockwise, we're looking down from the positive 1, 1, 1 axis. So our eyes, our eyes are looking, I don't know, here's our eye. And it's looking down this way, and it's rotating by theta degrees counterclockwise when we look from this direction. Not from the other direction. So what matrix does this? That's the question. Well, the trick is to think about how we can describe this in a simpler way in terms of the standard basis vectors. And one thing that we can do is we can look at this plane and come up with two vectors that are on this plane that are at a 90-degree angle with each other. So if you imagine this plane looking like this, and here's this point corresponding to origin, we can find two vectors like this that are at a 90-degree angle with each other. And then we can map those vectors, which are in R3, down to the xy plane. So we need two vectors that are on this plane. They need to be orthogonal to 1, 1, 1. So one vector would be like 1, 0, negative 1. Right? This vector, let's call it v1, is orthogonal to 1, 1, 1. And you can also take the vector 1, negative 1, 0. And we can take that to be v2. The problem is that these are not orthogonal to each other. They're both orthogonal to 1, 1, 1, but they're not orthogonal to each other. So can we replace v2 by something else? How can we find a vector that's orthogonal to 1, 0, negative 1, and 1, 1, 1? I guess we could take the cross product, right? This is sort of a last resort, but I mean, this isn't the only way to find two vectors that's orthogonal to these two vectors, but it's one way. So we get I hat negative 1 minus j negative 2 plus k 1. So we get negative 1, 2, 1. Let's just check that that works. No, I think I made an arithmetic mistake somewhere. There should be a minus 1 here. So negative 1 to negative 1. Yeah, that works. Okay, so this is correct. So v2 is orthogonal. So I have these two vectors that are orthogonal to each other. So notice that I have an orthogonal basis of R3. Let's call this vector 1, 1, 1 v3. So I have this vector these vectors v1, v2, v3. This is an orthogonal basis for R3. So if you take the matrix, so what I'm trying to do is I'm trying to find a linear transformation that will take v1, v2, and v3 to e1, e2, and e3. So I have these three, let's get rid of this. I have these three orthogonal vectors like this, right? And I'm going to map those three vectors to e1, e2, and e3 in such a way that v1 and v2 will go to e1 and e2. So I need to find a matrix that does that. Well, the matrix, let's say I take the matrix whose columns are v1, v2, and v3. So v1 is 1, 0, negative 1, v2 is negative 1, 2, negative 1, and v3 is 1, 1, 1, right? This matrix takes e1 to v1, e2 to v2, and e3 to v3. So what will the inverse of this matrix do? The inverse of this matrix takes v1 to e1, v2 to e2, and then v3 to e3. So let's say I apply this linear transformation to my space v1, v2, and v3. Well, then I'm going to get e1, e2, and e3, right? And now, when I'm rotating by theta degrees, when I'm rotating this plane by theta degrees, once I transfer v1 and v2 to e1 and e2, that amounts to rotating the xy plane by theta degrees. I'm basically taking this plane here. This plane is going to the xy plane. Right? And now my v1 and v2 went to e1 and e2. So I do step 1, which is I map v1, v2, and v3 to e1, e2, and e3. Then I rotate about the e3 axis by theta degrees. And then that plane, I have to map it back to the original plane. And that will be the rotation of that plane by theta degrees. Okay, so should I just write that down? So think of the rotation about the 1, 1 axis as first. It's a composition of 3 maps. First, map v1, v2, and v3 to e1, e2, and e3. Okay, then rotate the e3 axis by theta degrees counterclockwise. And then once we do that, then we map, okay, we map E1 and E2 and E3 back to V1, V2, and V3. And if you think about what happens if you do those three things, that's the same as rotating about the 1, 1, 1 axis by theta degrees. So this rotation, we're thinking as a composition of three linear transformations. The first one is to map V1, V2, and V3 to E1, E2, and E3. So that's this matrix inverse. Then we rotate the E3 axis by theta degrees. So we have the composition of these three maps. Rotating the E3 axis by theta degrees counterclockwise, well, that's going to be cosine. We know how to do that, right? We went over this. The first column is going to be cosine theta sine theta 1. So when we have, okay, so we're going to get cosine theta sine theta 1, and then the second column is negative sine theta cosine theta 1, 0, and then the last column is 0, 0, 1. And then the last step is to map E1, E2, and E3 back to V1, V2, and V3. Well, that's easy. That's the matrix that does that is the matrix whose columns are V1, V2, and V3. So this product, that matrix is going to rotate about the axis by theta degrees. So depending on your theta, you're going to get a different matrix in the middle, and then when you multiply them, okay, you have to do this calculation. You use a computer program to do this matrix computation, and whatever matrix you get, that's the matrix that will rotate about the 1, 1, 1 axis by theta degrees counterclockwise. Okay. So let's just summarize what we did, because this is a fairly time-consuming problem. The point is that to describe a rotation by theta degrees about a different axis than the x, y, and z axes, first you need to find two vectors that are on the plane. Okay. Now, do they have to be orthogonal to each other? In this case, it wasn't super important that they were orthogonal to each other, but the reason was because when you rotate the two vectors, you end up rotating the whole plane. Okay. So in this case, it wasn't strictly necessary to keep, V1 and V2 to be orthogonal, but I think to understand what's going on, it's easier to work with orthogonal vectors. So you have these orthogonal vectors V1, V2, and V3, where V1 and V2 are on the plane. Then you map those vectors to the E1, E2, and E3 axes. Okay. Then you rotate the E3 axis by theta degrees, and then you take that rotated plane back to the original plane. Right? And that composition will do the rotation. And you get this matrix. So that's how you would rotate about an axis that's not the x, y, or z axes. Okay, this probably will take some time to think about, but once you understand that this matrix composition really does give you the rotation, then you'll see that this is correct. Okay, thanks.